All right, folks, we'll go ahead and try to get started here. As you just heard, I just turned on the recording, so we'll be recording the class material as it comes through here, and try to get this back out on the website by the end of the week, so anybody can review it. Or if anybody has some partners who had to miss the class, they can make sure and catch up on it afterwards. So today, what we'll be covering is demand response and markets, and how these are used specifically in GridLAB-D. So I'll be giving this presentation today. My name is Jason, by the way. Frank Tuffner is also on the line, and he will be helping me out monitoring any of the questions that come across the forum here on the. So please feel free to use those and type any questions you have, or interrupt and ask questions as we're going along. Note that Frank's also managing the kind of muting and unmuting of speakers. That's really not supposed to be offensive. It's just trying to make sure that we don't have a lot of background noise and the voice over IP goes cleanly and everyone can hear us. But don't be afraid to raise your hand and ask any questions as we're going. What we're going to cover today. Basically, we're going to talk a little bit about what is demand response and the kind of wide world of DR, and specifically the approach that we are taking in GridLab and how we're trying to represent those type of responses and actions within the GridLAB-D environment. And then, of course, we'll go over the actual implementation of how we perform different types of demand response in GridLAB-D. So, very general, the idea for how we're approaching this in GridLAB-D is that this is a balance between demand and supply. Whether you're trying to maintain frequency or long-term, more like balancing reserves on your system, we're trying to represent this as a way that the load can participate in these type of actions of balancing the load either on a very, very short time frame or a longer time frame, whatever your need might be. So we try to design it to be fairly flexible to work across all these different time frames, but really to actively engage the load in the balancing process. So we accomplish this in here with a quote-unquote market concept. This is where the market module comes in. We've specifically designed this around a certain number of control strategies that we were interested in looking at. Specifically, two-way bidding, so that loads could bid into a supply and demand market, just like you would at the transmission level. Basically, the suppliers are bidding in the amount that they can provide and what they want to charge for it, and the demanders are bidding the amount they want to use and how much they're willing to pay for it. And then this market opens up, lets all the people into it, and then it clears this market, closes it, and delivers a closed or a cleared price back out to the rest of the consumers so they know how to react. All that said is that's far more complicated than most demand response schemes, like direct load control or even time of use critical peak pricing type of things. However, we accomplish it all in the same way, and I'll kind of show how that concept gets passed through to all the different control devices. But the basis of what we're trying to do is built around this market concept idea. Now, whether you use the control signals in a market construct, as in price, or the control signal is an index number of some kind, is irrelevant as far as the software is concerned. And as we get to some of the examples, I kind of show you, what we're trying to talk about there. It's a little bit more on how we're treating these end-use loads. So the idea is that when you start stacking up all the different buyers in the system, specifically on the end-use load side, you can stack that up to form a curve in economic terms, and then you can basically look at on the x-axis here. You have the quantity, basically how much power are these guys trying to buy, and then we can look at price on the y-axis there, and how much they're willing to pay for it. So you can look at the purple curve there being the supply curve. In general, this looks more like something that you would see at, say, the transmission level rather than the distribution level, but again, we'll talk about that in a little while. But really, it's the idea of looking at the demand instead of providing a inelastic function of demand, i.e. it doesn't matter what the price is, we're going to still use this amount of quantity. We're starting to treat demand as an elastic component and look at the ways that we can affect how those devices respond to certain price incentives and control signals. Again, just a little more background. Once again, it's the idea that because load isn't currently a very active participant in balancing and other type of peak system reductions and things like that, except for in very directed manners, like direct load control or critical peak pricing. We want to start exploring some of these different ways that we could try to control the devices, and specifically looking at ways that we can mitigate things like peak rebounds or synchronizing of devices at the end of a critical peak price period, and how we can start mitigating some of those different things. Again, this is just a little background, so I'm going to skip over this. I think everyone here kind of understands this concept that if you're trying to reduce peak, then you can look at your 5% of your year, or excuse me, 5% of your hours in your year is about 75% or about 25% of your cost, because you have to build your system up. So reducing the peak has a lot of value. But then really what we want to get to is that in order for demand response to be effective, you have to have some form of control input. Now, whether this is a very passive form of control, whether it's a very simple time of use type of pricing, or it's much more complicated like real-time pricing or closed loop direct load control. Either way, there is a control input, and how you push that control input in is kind of the interest level of what we're trying to look at here. And so, some of the things that we've been looking at with it in GridLAB-D specifically is looking at for peak load reduction, regulating services, some kind of emergency conditions where you can use like load shedding type of ideas, but instead of using load shedding, using a demand response type of signal. And then really what we want to try to look at is how to make these devices participate in multiple ways. So if you're looking at direct load control just for, say, emergency conditions, while that provides a lot of value at the system level, it may not provide enough dollar value to justify the cost of the outlay. So part of what we're able to do with GridLab, and part of the fun of what we're looking at, is how to merge these different things into different weighted optimizations to say, should these devices be participating in peak load reduction versus regulating services versus other services at any given time, and how is the best way to capture that behavior and effectively reward the people who are participating in each of the subsystems there. So it's some of these are fairly intuitive, but we'll go kind of through them really quickly. Peak load reduction, we're obviously a very nonlinear system here, so if we can reduce the peak load, we can greatly reduce our I squared R losses and try to reduce the peak unit efficient or less efficient peaker units. So we're looking at a number of ways to try these peak load reductions. I think everyone kind of knows these type of things. I'll skip over a couple of these here. At some point there is what we'll call an optimal peak reduction, which would be the perfect flattening of your load. That is obviously fairly difficult to attain, but you want to try to approximate that as well as you can without overly influencing or overly affecting your customers. But it's not necessarily realistic that you're going to be completely flattened, so we're looking at what is the most optimal way of reducing without overly engaging your consumer response. I apologize. I'm just kind of going through a little bit of background here of what we're trying to accomplish inside of GridLab to give everyone a little bit of an idea. With the regulating services, again, we're trying to look at generation load balance on the order of seconds to minutes to make sure that we're keeping a balance across the system. And one of the approaches is that you can use demand response. Say, water heaters are a pretty classic example, but clothes dryers are also seem to be pretty effective at this. Is that you can very quickly reduce or increase your load by turning on and off the heating coil in those devices to do short-term regulation type of services. And then, of course, emergency conditions. How can we do either use demand response signals to either prevent the type of blackout type conditions, or vice versa on the side where we're trying to recover from a blackout situation? Can you use these demand response signals to prevent kind of your surge capacity on your cold load pickup? And these type of things, you could use demand response signals to do that, rather than try to say cascade your turning on of your feeders and things like that. So really what this was all born out of, and where it was originally designed to start from, was with the Olympic Peninsula demonstration project, which this project was actually the birth of GridLAB-D and the reason that GridLAB-D was created in the first place. So for those who aren't familiar with this project, this was a demonstration on the Olympic Peninsula in Washington State, done in 2006, 2007. And what this was is that there was a single transmission line going out to the Olympic Peninsula, surrounded by water on 3 sides. The transmission line itself went through a national forest, so there was not a lot of availability to expand capacity. So the idea was to take a look at a way of, instead of expanding capacity or putting in a new transmission line, to look at ways of reducing demand purely on peak to bring this back, to bring this area back into requirements for its peak capacity. So this was the first example of an experiment using what we call now transactive controls or transactive markets. The idea being that each of the devices in this market, in this case it was hot water heaters and HVAC systems, or air, in this case heaters, because there's not a lot of air conditioning in this area, but heaters and a few other devices participated in this market experience where effectively they bid how much they wanted for, how much electricity they wanted and what they're willing to pay for it. And in turn, the market decided how much power was going to be allowed to flow excuse me, down this transmission line, and was able to provide a balance to say, okay, what's the optimal price at every 5-minute interval to make sure that we don't exceed our capacity limits. We also had a number of DG and storage that participated in this. So, for example, there was some diesel generators at a backup for a commercial building that also participated in this market. There were some large loads like pumping stations and things like that. But this was really kind of the first demonstration that if you wanted to apply some kind of external constraint on the system, in this case it was capacity limit, which is given by this green line right here, that we could use a market mechanism to limit the load behavior in a way that it would shift the load to be below capacity. This one's a good example here because this is actual raw data from the demo itself. So we could see, this was the blue line is the what would have happened, the red line is the actual load, and you can see, during the first 2 days of a very cold event, it responded very well. But of course, by the time we got to the 3rd, 4th, and 5th day of a very, very cold, this was something like in the order of teens and single digits Fahrenheit. It was very cold. By the 3rd day of a 5-day cold spell, people just kind of gave up. And we can see that reflected in the way that they started responding with their devices. So this is one of the takeaways from this, was that the consumer interaction is just as important as the way that the demand response is modeled, the way the demand response is set up. So the question that came back from this then was, well, that's great. That seemed to work pretty good in the Olympic Peninsula, but what would happen if we took it to California, Minnesota, Florida? And looking around at all the different tools that were available, there wasn't one that was available that could really answer that question. So hence the reason that DOE started investing in GridLAB-D, was to try to answer this very specific question and look at all the different what-ifs. If you wanted to move this to, say, a different market area, you wanted to set up new rules in the market, you have the different climates, and now you have different behavior. So really looking at how this would move across the system and scale to other locations. And we'll get a little bit more into some more of the details of the market of this market system here in a few minutes. So one of the other things that we've worked on in the past is looking at how to mitigate the rebound that occurs after a demand response event. So this is a very important phenomenon. Right now, that's typically managed by either rotating a critical peak price, call them bins of people, or only calling a certain portion of your population, so that you're relying on part of the diversity within the system to not create too large of a rebound. But really, what this is caused by the fact that when you look at the side of a household, if you normally want to be running your HVAC system at 60% duty cycle and then you reduce it for 2 hours and hold this back, you can see by asking for example, this is a 5-degree setback program, I think for something like southern Texas. You ask for 5 degrees, you get that great initial response. After an hour and a half, you're basically almost up to your original duty cycle, maybe just slightly lower because of the temperature differential. Then at the end of 6 hours, when you release it, of course, you have to go back up to 100% to recover all the basically the lost stored energy that's in the system. And it takes a long time for this type of thing to settle out. This is a pretty simple model, but basically shows that it takes about 12 hours after. When you're looking at a 6-hour critical peak price event, it actually takes about 12 hours for that system to recover from that. And not only that, but you're not even getting your full bang for your buck, because you only really get response the first hour or two. So of course, there's obviously a lot of other strategies that are more intelligent about that. Doing reduced duty cycles over the course of the entire 6 hours or something along those lines. But really kind of showing the effects that we're trying to model and capture. And this goes to the whole reason why we've created the residential models that contain all of these pieces that allow us to look at how a event signal will actually shift the behavior inside of that home and therefore affect basically the physics that reside inside there, and then look at the way that managing of that recovery at the end and try to capture all those different things. So it's just another example of this. This was some work we did with some partners from NRECA, basically looking at, they wanted to understand what their max capacity was for reducing load. And so again, this was done by rotating, this is time of use prices, was actually rotating critical peak prices, basically going through and creating 4 bins of customers and rotating them through so that they got the right mixture, so we could get basically a perfectly flattened load. And it was able to show that the potential reduction is about 11.5%. Again, this was in a very warm South Texas area, so 11.5% was actually pretty surprising on that. And then one of the other things we are able to track because of the way that we've built these models is the way that these demand response events affect the customer themselves. So you can see in this case, if we look at this response, this is corresponding to the same event that we just looked at. The blue line here represents the average thermostat set point throughout the day for a whole population of customers. I think this was something in the order of 500 customers. So you can see, of course, there's your morning setback when people go off to work. Some people raise their temperature a little bit, and then as people come home, you start trickling it back down. Now you can see here, this is the demand response event where we basically requested them to do up to 5-degree offset on their thermostat, and you can see the difference on there. So some customers are experiencing a significant shift in their thermostat set point, but in this case, on average, about 2.5 degrees. And so it lets you lets you track the way that the system is evolving. Not only naturally, but also by how your signal is actually affecting the evolution of that system. Sorry, I apologize. I'm afraid I'm catching a cold here, so I've got to stop and take a drink every couple minutes. So a little bit more of a conceptual model of what it is we're trying to accomplish. Just a few more minutes of this, and we'll get into the actual how we do this in GridLab. So the type of load control that we have been looking at specifically in GridLab is direct load control. So we support that on a number of devices, anywhere from HVAC systems to hot water heaters. A couple of our other smaller appliances, we do direct load control. The direct load control is actually probably the simplest one to model inside of there. Demand response, in more classical terms, is time of use, critical peak pricing, and real-time pricing. This is both a passive response to a price signal or to what we'll call a double auction market, or this idea that I was talking about with the Olympic Peninsula demonstration. And then we're also looking at a number of different types of distributed controls, aka things like grid-friendly appliances where you're responding only to local information like voltage or frequency and performing some kind of response doing that. So obviously, direct load control, we're talking about a direct control path to the appliance, what we call a controller. And so, these are typically the type of contract that's signed ahead of time. Consumers are aware that there will be a event, typically, given some kind of notice, and typically given some kind of rebate for allowing this type of control. Obviously, this is a quite popular form of method because it has what I call the big red button. Basically, for the most part, utilities know what their response is going to be when they push this button. Now, setting that system up so that they get the response that's desired can definitely take some work, but for the most part, it's a fairly well-known and fairly well-understood type of control. We have time of use, which becomes quite interesting in terms of how this interacts with the social aspect. So this is purely a price signal over a long-term scale that is trying to affect the way that customers consume electricity. Now, those have a bunch of different aspects to them, whether it's just a purely price change only, or typically this is also integrated with new forms of information to the consumer, which then affects greatly affects how much they will actually respond to this type of change in price signal. And then again, you can also add on further hardware so that it can actually either automatically respond to the price change, or, for example, programmable thermostats that can be programmed to match up with the time of use pricing. And so capturing not only that the technical aspect of the modeling and things like that, but trying to capture the way that the social aspect of it, basically the way that people respond to these different things, becomes a little bit of a challenge, and becomes actually part of the fun part of this. So we'll go into how we've tried to represent this, and of course always open to new ideas on that one. Again, if you're using time of use, critical peak pricing especially, you can have an overabundance of what's called the rebound, or a kickback, or a number of other different options for it. This is obviously a fairly overblown case for an example, but this is with a large population of consumers with everybody responding. You see you get great reduction, but as soon as you release the signal, everyone goes, "Ooh, I'm hot. I'm going to turn my air conditioner back on." So you get a giant spike as everyone tries to cool their house back down in the evening. This doesn't exist in all locations, but it can be fairly common, especially in areas where there's high moisture content and it takes a long time in the evenings for things to cool down. So things that we're trying to adjust when we're looking at here. So we're talking about the HVAC system. We're looking at thermostat control for the most part, but we also have some direct load control, duty cycling, those type of things. But it also has things like looking at the hot water heater. Of course, you're trying to lower the temperature set point. So basically, this means that if you want to perform some kind of DR, there's a thermal mass or some kind of process that has to be deferred. And so by deferring that process, you now need to make it back up at some point for the most part. So it's a question of how this process is being deferred. So the models that we've created, specifically residential, appliance, those type of, they're really like trying to drive a simulation that's process-oriented to say, well, okay, we can defer this process, but there is a payment for that process now. In some cases, that payment back may be very, very small, say, for example, in a clothes dryer. But in something more like an HVAC or an AC system, that may be a fairly significant payback. And of course, like I said again, time of use critical peak pricing can be implemented in kind of two ways, both socially or in hardware. We are trying to make it flexible enough to combine both of these into GridLAB. But one thing that with time of use critical peak pricing that's a little bit difficult is it's not always reliable in terms of if you don't get as much response as you need, or over time consumers don't respond as much as they used to as they get used to the new pricing system. And of course, if there's poorly designed hardware implementations, then you can start getting rebounds and things like that. And then so one of the methods is to look at real-time pricing, of course, with double auction. However, that has its own fallbacks, which is it's fairly hardware intensive and can be a little bit complicated. In some cases, it can be overly complicated for consumers for whatever gains you're trying to get out of your system. So again, critical peak pricing, we'll go ahead and jump over this. We've already kind of talked about this here. So we get to the real-time pricing program. So the way that we've implemented this is to look at it, to basically look at price changing every 5 to 15 minutes or every hour, whatever whatever your flavor might be, and then looking at how that might be implemented in hardware. Because the idea is that looking at real-time pricing, we're assuming that for the most part consumers can't respond to that type of level directly, i.e. they're not going to be shifting their behavior. So this needs to all be done in automation via hardware. So whether this is a smart communicating thermostat or a home energy management system, whatever those pieces might be, when you're talking about real-time pricing, we're looking at much more of how this is done in hardware rather than the consumer response to it. So the advantage of real-time pricing is that you can, one, you can merge a number of different signals from across the power grid and look at the ways that these costs would be added up and passed on to the consumer. And you can also look at, it's a much more accurate reflection of what the current price of energy is. And not only the price of energy, but the price of delivering that energy. Now, of course, again, that adds a layer of complexity, and there's a lot of questions about how accurate can you actually be at that type of time scale. That's kind of the things that we're trying to explore. Again, we've kind of hit this, so I'll skip over this here. And then the RTP double auction market, which is our big push and the reason that this model was actually originally created in GridLAB. I'm going to go a little bit into more detail about how this is trying to work and how we've addressed it, because it will kind of expand, or it'll kind of define the entire envelope of what we're trying to do. So the idea is in a double auction market is you're trying to prevent things like your rebound. You're trying to get the exact response that you need for any given event, rather than trying to determine what those needs might be, say, in a centralized direct load control type of a manner. It's much more of a distributed approach where you can just put some constraints on the system and allow the system to determine what the appropriate price signal would be to match those constraints. So this is what we'll call a true double auction market. So both the end-use loads and the supply are bidding in their portion of their either demand or supply, and creating a market which is cleared. And inside that market, certain constraints can be put on to extract certain benefits. Obviously, this type of thing requires a fairly significant communication system. We're talking about two-way bidding, so communication in two directions. And one of the things that we're trying to explore is what are the requirements of that type of system, and how much communication do you actually really need to make it work. So we'll get a little bit into some of the meat of how this works here. And again, I'm approaching this from the most complicated form of what we're doing, and then we'll narrow in on some of the more specific examples of, say, for example, direct load control. But to kind of give people a picture of this, inside your market, you have buyers and sellers. So, for example, this buyer right here might be someone's air conditioning system. This might be somebody's hot water heater. This might be somebody's clothes dryer, whatever it might be. But they're providing the amount of power that device will consume, and that's usually an estimate. It's not not necessarily a perfect reflection of the real world. It may be nameplate capacity, or it might be a measurement from the last time it ran. And then we're looking at how what their willingness is to pay for electricity to run at that period of time. And so, and like I said, we'll go into a minute here about how we've automated those type of approaches. But really, what's happening is all the devices in the system are forming this portion of the curve, declaring how much they're willing to pay for certain amounts of electricity. And on the seller's curve, we're looking at things like, for example, this might be a diesel generator or maybe a wind turbine or something like that that's saying, well, here's how much power I have to provide. Here's how much I'm willing to sell it for. Inside the auction, these are all accumulated together, and some kind of balanced market clearing price and quantity are formed. Now, constraints can be put on here. So, for example, you could put a constraint, say, right at this level that says, well, that's my feeder capacity. So we can't exceed this quantity, in which case the price would be elevated to prevent that type of occurrence. So the way that we accomplish this in GridLab is we have two sets of objects in the market module. The first is what I'll call the auction-based. So these are auction and stub auction. And really what these are, they are kind of the centralized control device, for lack of a better term. They're the device that collects all the information, broadcasts it back out to the other devices. And in the case of a two-way transactive bidding market, the auction is actually looking at ways to formulate all the market curves and calculate what the optimal point is for within your constraints. In the case of a stub auction, which is looking much more at what I'll call a passive market, this is a purely reactive type of market. The market doesn't actually collect bids in any way. All it's doing is broadcasting a price or broadcasting some kind of signal. So these get matched up. We have auction and controller that are really designed for working with some of the transactive bidding structures, and then we have stub auction and passive controller that are looking at fairly purely just respond to prices type of, they're not doing a two-way bidding system. One note of that is that because passive controller can respond just to prices, it can be used with an auction also. But really this gets divided into, if you're looking at your auction, you're looking at receiving and transmitting bids. Stub auction, you're just sending out information. Controllers are going to be not only receiving information, but broadcasting information back out to the auction, while passive controllers are just going to be receiving information. So a little bit more about what these do. So generally the way we would build these is on a single distribution feeder, we will have a single auction object. That's not required. You can have multiple auctions on a single feeder. we have no way of communicating between these different auction objects right now, so they are basically two standalone auctions. But really it's there to collect bids, clear information, deliver clear prices back out to these control objects. And if you're doing something like a time of use, critical peak pricing, real-time pricing, whatever that might be, you'd attach a player that would put some kind of boundary condition on the prices. And we'll go to that in a few minutes here. The controller objects are much more of like a distributed control device. They are going to be attached to each of the objects that you're trying to control throughout the market. So you may have hundreds or thousands of these on a single simulation. But really what they're doing is they are to interpret the information that's coming from the auction. They will be attached to, say, something like a thermostat or a hot water heater or any other type of load. And it's there to modify the behavior of those loads in response to that price. So for example, a thermostat controller might be moving the thermostat set point up by 2 degrees. Or the hot water heater controller might be moving the set point down by 10 degrees. So these type of controls. And then in the fully active market where we're doing two-way bidding, this controller will also be looking at the states of the loads. For example, looking at the hot water heater, is the hot water heater on? And from that, formulating some kind of willingness to continue running. I'm sorry?
Finished. Hang up or press pound for more options.
Sorry, is everybody still online there?
I was just going to say, is the meeting still going? Looks like everybody's still in, so.
Okay, well, good. Looks like everyone's still on, so we'll continue going there. Sorry about that. This controller object is not only receiving information from the auction, but it's also going to be sending information back to the auction about this device, this particular device's willingness to participate in the market at any given price. So, kind of give you an example of what these auctions might look like. This is an example of a stub auction object, and really, like I said, basically what we're looking at doing here is basically broadcasting prices. So in this case, we're looking at a player that is bringing in a certain price. It's looking at current market clearing price is the property that we're feeding it into, but effectively we are trying to send that information out as a broadcast signal. You can see here it's updating every 300 seconds, and then in this case we're doing some recording. One of the other things that these auctions do is also collect a lot of statistics about the way that the market is behaving. So in this case, we're looking at the last 24 hours, the average price, and the last 24 hours, the standard deviation of price. And we'll go a little bit into that here in a second. Of course, in this case, the stub auction doesn't actually form a market and or form an auction or clear any type of market. So really, this is just a broadcast device. So when we look at what we'll call passive controllers, this one is, for example, a graphical representation of what the controller on the HVAC thermostat might do. Again, this is a price-based response. In this case, we're looking at the customer's desired thermostat set point. So say this might be 75 degrees. When price is average, so basically when we look at the last 24 hours of price, if the current price is exactly on the average, then the customer would be at a set point that is exactly their desired set point. However, if the price clears at a lower price, then the idea is that it is more desirable to consume electricity at that point, so the set point might be moved to a lower set point. In this case, this is a cooling system example. So, for example, if this low price comes in at something like half of the average, then maybe we're going to move our set point down by 1 or 2 degrees. Now, the way that the consumer is able to work with this device is really they have a simple, what I'll call a slider bar. Basically, they can go from comfortable to economic, and what that does is affect the slope of this line and affects the limits of Tmin and Tmax, so that as you become more comfort-driven, you would basically go to a point where your desired set point will always just be desired set point, no matter what the price is. So this is really just a way of interpreting a current price and translating that into a certain desired set point. When you look at the way a single individual unit might work, it's not a perfect solution, but when you look at and by perfect, I mean, the devices may not respond exactly the way that you would predict, but when you look at the aggregate population, it has the effect of reducing load when price is high. So in aggregate, these type of things seem to work out quite well. Again, the whole reason for creating these type of models in GridLab was to start to explore some of these different ideas. So a little bit about how this passive controller is built in the GridLab. And again, this is for this very specific example. Again, it's not designed to send out any type of bid signal to a market. Of course, it's only using unidirectional type of communications. But in this case, what we want to do is basically we're trying to represent this graphical curve inside of a text-driven object. So we have what's called a base set point. So this is basically what would for a price signal, what would the consumer's set point be? So in this case, we have a schedule called cooling 3 that's probably doing something like 72 degrees in the morning and 75 during the day, and then back to 72 in the evening. We have this control mode called ramp. So control mode is what we use to activate all these different control modes. So if we want to move from, in this case, it's a ramp mode for this HVAC system, but when we move to some of the direct load control ones and some of these other pieces, we will change this control mode to activate it to the right type. So sensitivity is this slider bar that I was mentioning. So in this case, a value of 1 indicates extremely responsive, where a value of 0 will indicate not responsive. We have what's called the expectation object. So this is basically which auction do we want to look at. So in this case, we have an auction that's named Market 1, and we're looking at this object. We're looking at a certain property in there. In this case, we're looking at the average price of the last 24 hours. And the reason we're using the value expectation is because we're using the last 24 hours of data as a predictor for what might be happening over the next 24 hours. So in this case, our expectation is that the prices should remain somewhere around the average of the last 24 hours. Now, of course, you can change this expectation object or this expectation property to any object and any property that you would like in GridLAB-D. But this is specifically built for this type of market system. So just be aware of those type of ideas. You'll see that this object is fairly complicated to put together for what seems like a pretty straightforward control. But the reason being is because we designed passive controllers to respond to just about any signal you can think of. So in the case of, say, like a frequency response, you could actually make this expectation object, say, what we call a frequency generator, and the expectation property could be the current frequency. So this object is designed to be very flexible for a number of different testing purposes. Then we need to tell it which properties we're trying to control. In this case, we're going to control the cooling set point. We also need to tell it how we're going to control the current state of the device. So in this case, what we're doing is we're using what's called override control. So this will allow it to, when it adjusts the cooling set point, rather than just passively responding there and moving the thermostat set point around, if we activate this flag here and connect it to the override property, then what will happen is that when the thermostat moves and it should turn off because of the price, then it will command it to override that and actually turn the device off. So it's a little bit more of a combined direct load control and non-direct load control type of response. And we also want to look at what the current situation is. So we're doing comparisons of past information to current information, or this could be, this could be predicted information versus current information. And so we want to observe, again, we're going to observe the same market in this case, but the property inside that market that we're going to observe is a property called current market clearing price. And this is basically what the current value is at this time. So we're going to take a look at it, and this becomes a reflection in this last graphic of P clear. So this P average becomes the expectation value, and P clear is your observed value. And then we attach a couple of other properties to look at that are also linked to this market one. So we're looking for, again, the last 24 hours average, last 24 hours standard deviation. And then right here, these values set the ramp rate on this curve right here. So basically, you're setting the slope of this device. And notice this is a bilinear. So we actually have a breakpoint here at the upper and lower. This area represents pre-cooling. This area represents deferred cooling. So if you want to do something like turn off your pre-cooling, which is quite common, and not allow for that, but only allow for deferral, then you could set that up here where you could say, for example, range low would now be 0 rather than negative 1.5. And the range high is basically how high are you willing to respond to this. So this basically becomes the willingness of the customer to respond, how much they're able to respond, how much they're willing to let you play with their thermostat, basically. And then these ramp rates is basically how fast you respond to it. So if we look inside here, here's an example of the price player that you might use to feed into this stub auction device. Again, it's just like a standard player, but we're looking at creating our time, giving a price. In this case, it's in dollars per kilowatt hour, and then feeding that information directly into the market, and then broadcasting that information to all the different controllers. Of course, this is in 1 hour time steps, but you can do it in larger or smaller time steps, however you might want to do it. One thing that does have to be given is that all the time quantities in the controllers versus the auctions versus your players need to be all on the same scale. GridLab won't specifically check for that because there are a few reasons why you might not want to, but in general you want those all to, say, in this case, be at 1 hour intervals. You wouldn't want to do, say, control at 5-minute intervals but only update the price on hour intervals. You might get some very strange results on there. So one of the other things that we can look at, and so the reason this is here is because this was an example specifically using these passive controllers in the way that was just set up here, is we can look at the way that the population statistics are affected by different controls. So if we take a look at it, any HVAC system, for example, has effectively 4 operating modes. Obviously, there's a few more than that, but 4 general modes. One is off, obviously. One is cooling. One is heating, and then heating auxiliary, i.e., you basically aren't heating fast enough with your heat pump, so let's turn on a resistive heater. And of course, your control signal is going to distort these populations statistics. So we want to look at how those might occur. It's kind of hard to tell on this graphics here, but you can see here, this is a cooling example again. You can see the number of devices. In this case, it's a population of 1,000 devices. At any given time, we reach about 305 cooling devices on, and then as it cools off, we can quickly see them all starting to turn off. This happens to be kind of a shoulder day in Seattle, so there's not a lot of air conditioner response there, and it cools off very quickly. But you can see by sending in a certain price signal, This one, I believe, is on a 5-minute or a 10-minute interval. You see one that it starts to cause some synchronization of some of the devices because, say, for example, if the price swings high, then low, then high, then low, then you're going to have synchronization of devices. And then, but you can also see that there is a reduction in the number of devices on, somewhere in the order of about 2 or 3%. So you can start, this is not really a compelling example, but you can start looking at the way that these different things affect each other. Excuse me, just one second. So the next one we'll look at is direct load control. So we have a number of different direct load controls that we're representing in GridLab. So the HVAC system, one of the ones that we're currently working with is what we'll call direct load cycling, i.e. modifying the behavior of the HVAC system and setting the duty cycle of that HVAC system. So this is a fairly simple approach at this point. It could easily be expanded to something much more complicated, but effectively what it's doing is it's looking at what the duty cycle is of the HVAC and trying to reduce it. Really, you activate this by turning on a certain direct load control, and then we have a certain direct load controlled mode. In this case, it's cycling. It's looking at what the on time versus off time. So in this case, you're looking at something that's going to be on the order of about a 40% duty cycle, and it will enforce that 40% duty cycle. As soon as it sees a price coming from the market that happens to be above this price. This price in the way that we've designed it is equivalent to the critical peak pricing. So as soon as it sees a critical peak price or anything above this price right here, then it will activate this cycling mode. So again, it's looking for the for specific market, and for this case, we're looking at the past market clearing price. So we're actually delayed. We're responding at 5 or 15-minute intervals behind what's going on in the auction. There's certain reasons you may want to do that. This is more just used for an example. And then, again, we're using an override because in this case, we're actually going to be telling the device, no, you must turn off when I tell you to, rather than just trying to move some of the set points or something along those lines. So for water heaters, we have what we call a probabilistic mode, and this can either be a very gradual type of direct load control, or we can use it as immediate type of direct load control, and I'll talk about that here in a second. But really what we're looking at is we're using a probabilistic mode that says basically as price increases above a certain level, again using average price as the basis for this, as price increases above a certain level, then there is a probabilistic chance of turning off hot water heater. As the price goes higher, that probability gets higher and higher, eventually until you reach a certain maximum, which is usually about 3 standard deviations above your current price. At that point, all hot water heaters will be turned off. So it's really kind of a mixed, distributed, and centralized control, relying on the devices to react in a way that's dependable. So in this case, again, what we've done is attach this to a market system, and we're looking at the clearing price or a broadcasted price. We're also looking at the standard deviation, so we know how high the current price is compared to the average price. And then we have what's called this comfort level. Effectively, that's looking at how fast are we going to respond. So someone who has this high of a comfort level, so basically infinite, says that as soon as price gets, no matter what price does, I will not do anything. As that comfort level approaches 0, then that would be something more along the lines as price goes above average, we're very willing to participate and reduce my load when this price signal comes out. So this is a way that you can set this up so that you can basically either do this very probabilistic mode where you're kind of trying to get a subset of the population to respond as a function of the increase of price, or you can basically adjust these comfort levels to let you do what I'll call true direct load control, where when a signal goes out, say a price, you basically go from a price of average to infinite, then this will react like a true direct load control program, big red button that just turns off all the devices. So that's how we've approached it and how we've been able to kind of merge these two different methods inside there. And again, I'll go into examples and show you where we have a lot of these set up so that you can take a look at here in a few minutes. The other one we've worked on is pool pumps. This is a very, very simple approach to this. It was kind of a little bit of an off-the-cuff first try at it. So in our object zip loads, we've created a cycling model that allows you to set the duty cycles and run times to make it look like a pool pump, and try to operate it in a way that's similar to those. And then this effectively lets you perform direct load control in it. So there's a couple different modes of operation. In this case, DLC mode off. It does just that. It turns off the pool pump until you allow it to turn back on. Once a certain price has, once the clearing price of the market has reached this price, it will just command the pool pump to turn off. We have another mode in there, which I apologize, I don't remember the name of it right now. We can look it up here in a few minutes. But it will be a little bit smarter than that, and it will look at how much runtime you have deferred over, say, a 6-hour period when you were in the off mode, and you should have been on, and it will kind of try to readjust the duty cycle following an event to recapture that lost runtime. So again, this is a fairly simple model, but it allows us to do some very easy on-off type of control. So this might be a good place. Let's go ahead and take about a 5-minute break, and I'll admit this is mostly for me, so my voice can recover for a minute, but also if anyone needs to run to the restroom or anything like that. So let's get started here. I'm showing a time of 9:02, so let's get started again at about 9:08 or so. But if there are any questions, please feel free to ask them. Just taking a mini break. So. Okay, everyone, thank you. I appreciate that. I was able to take a cough drop and recover my voice there for a second. Hope everyone had a chance to catch up on email or whatever else was necessary there. But let's go ahead and get started here. Probably don't have much more than about 30 to 40 more minutes here, if that. But we'll kind of go through this, and then we'll go through a few examples. We'll walk through some of the different demos and things like that we have available from the class material, and then show you a couple links for where you can get even a little bit more complicated examples. So the next piece that we've been trying to represent in GridLab is the consumer response. So basically, when you look at time of use, critical peak pricing type of things that are or are not automated, we want to understand how consumers are actually going to change their behavior as a reflection of this price, and how this might be represented in code effectively. So one of the things we want to look at was basically looked at what's called the price elasticity model. It's based on some models that are used in PRISM, which is a kind of high-level economic model that Ahmad Farouqui and El Wood have used to kind of create a very empirically based type of data that says, how much do we think the consumer will respond to this amount of pricing change? So this is, again, very much driven by the way that that data was captured during certain pilot studies. These guys have worked with a number of different utilities to try to determine what these values might be. It's obviously quite different from utility to utility, from different control mechanisms to the next. But really what they've done is done a very nice job of breaking it out into effectively, if your price changes from a low time of use price to a high time of use price, the amount of that change affects the amount the customer responds. So if you have a ratio of, say, 1 to 2 from your low time of use price to your high time of use price, you might get a certain response, whereas if you have a ratio of 1 to 5, we get quite a different response. It's all about what's that dollar amount that will push consumers into providing that amount of response. And the higher that price is, the more response you'll typically get. But again, these are all driven by empirical studies and are not necessarily perfectly reflective of what might happen. But the way that the price elasticity model is, there's what's called two different elasticities. One is what's called substitution elasticity. This is basically how willing is the customer to shift their energy usage from on-peak to off-peak. So I call this deferred energy usage. Basically, when you go from a period of low price to high price, if you look at the blue line here, this would be your base load. But then when you go from a time of use price, you can look at the way that the load is increased in the off periods and decreased in the on peak periods. But at the same time, over the course of the day, the energy consumption is exactly the same. So this is really just looking at how consumers will move their load from one time period to another. The second is what's called daily elasticity, and this is the effect of how consumers overall will decrease or increase their daily energy consumption in response to a change in price. So effectively, because you have moved from a fixed price to a time of use price, or you have moved from one form of time of use to a different form of time of use, the way that consumers see the consumption of electricity is different, and that generally has the effect of reducing energy consumption. Again, this is purely from collected information from field studies. So this really only works if you're moving from one known price structure to another. But if you were, say, moving from one unknown price structure or one known price structure to an unknown, you might not be able to get as much information out of this as you like. But really, in the end, you combine these two so that you get the substitution elasticity and the daily elasticity, and combining these two, you can get a new load shape. Now, this applies, as you can see, to a load shape itself, so at the feeder level. This doesn't necessarily reflect exactly what an individual consumer will do. So we've had to make some modifications to this to try to represent this inside of GridLAB. So in this case, we create this again in a passive controller, where a price signal might be coming out from either a passive, stub auction or an auction, and then this controller gets attached to a zip load, which is our very generic load shape generator inside of a house. So this is not used to, say, look at the effects on your HVAC system or your hot water heater, unless you include those in your load shape itself. Typically, we use these to represent other loads beyond the HVAC system and the hot water heater. Currently, it's built to represent either what I'll call 2-rate or 3-rate time of use plus critical peak pricing, so your number of tiers. Now, each rate period has its own elasticity, and they're always in comparison to the lowest rate period. So basically, if you're looking at these different elasticities between different price levels, then it's always going to be based towards what that lowest price is in your system. Just the kind of units here, negative elasticity represents less energy consumption, either during the entire day for daily or during the critical price period for your substitution elasticity. In this case, we update that load change every market period. So if you set a market period, in this case, of every 15 minutes, that reduction will go and look at the current price of electricity and calculate what that reduction or increase in load might be at that given time. So you can see, to build this elasticity model takes a lot of connections, but really what it comes down to is, this is just copy and paste. So you just bring all these type of things in. Really, we're connecting it to our correct market, looking at the correct price. In this case, we're looking at either a 2-tier critical peak price period, or if you would activate this as false, then it's a 3-tier plus critical peak price. This always gets activated to tell it that we need a multiplier on the load. So, for example, what it's doing is it's looking at this at the zip load, and there's a property in there called multiplier, and that's how it's accessing it and shifting the load from its base load. You can either linearize this elasticity or not. So over short time periods, it's very easy for calculations to linearize this. It does change your values or your answers slightly, but it significantly increases speed because of all the built-in inaccuracies in these models. A little bit more doesn't seem like it's really hurting anything. You can activate critical days, so you can tell it what days will be the critical days. In this case, this is just a flag of 0 and 1, so that it knows. Basically, this is the way so that it can react to consumers got the 24-hour ahead of time call that a critical peak price day was coming. So it basically starts responding early rather than only after the event. So you go, for example, on a critical peak price day, you'll get a slight increase in your load during the mornings and early afternoon, and then, of course, a significant decrease during the critical peak event. So by setting this flag on certain days, then you can start doing that predictive value. This is just setting up the rate structures themselves. So in this case, it's your first tier is 12 hours, your second tier is 12 hours. Yes. So sorry for the question in the forums there. The critical day is literally just a a 0 or 1 and a timestamp. So in this case, this is coming through a player file that would literally look something along the lines of like this. Let me type it in here. Just something like that. So that would be, on the first day of January, it's not a critical peak price day, and on the second day of January, it is. So you just feed that in as a player value. So yeah, sorry, that was a good question. And again, that's just the way that the market or this controller knows that it's coming up to a critical peak price day, so that it can capture the pre-critical price period type of information and response. So again, this is setting up the tier both in terms of hours and price. Notice that this is a 2-tier time of use plus critical peak price. So the first 2 tiers represent time of use. The third tier represents the critical peak price. And on a day where we go from in this case, when we go from a non-critical peak price day, which has 2 tiers, we'll go to a critical peak price day that will also have 2 tiers, represented by the first tier price and the third tier price. The second tier hours and price are ignored on that critical peak price day. So basically it's a replacement. You replace your second tier time of use with a third tier critical peak price. We have all the different configurations in there, at least that I can think of, where you can either, you can use your first 2 tiers and then add a third tier on that day. You can replace your first tier with, you can replace it like we do here. You can do 3 time of use tiers and then replace the third with a critical peak price. So it supports all of those different ones. And then because we're looking at a comparison of what consumers are shifting from, we also need to tell it what the old price was. So in this example, the old price for all the different tiers, it doesn't matter which one, was a flat rate. It was a base price of 12 cents a kilowatt hour. And now we're moving to a time of use price of low of about 7 cents a kilowatt hour. The second time of use tier is about 14 cents a kilowatt hour, and the critical peak price is quite high, 70 cents a kilowatt hour. But notice that's about a factor of 1 to 2 to 10, and it's that factor that actually is determining how these are going to respond. And then we actually specify the elasticity values. So in this case, we have about a 13% elasticity on the consumer himself, and much lower substitution elasticities, and that really defines how this particular passive controller will respond. Now these are the values that, of course, have the most kind of flexibility in them, to use it, to put it nicely. So the way that we have approached this in the past is looking at some of the work that these guys have done at Prism, and they have kind of provided a lot of this information out to the public. You can go and you can find elasticity values that tend to match up with your type of pilot that you may be looking at, or your study that you might be looking at, and you can extract this information where, say, for example, this might be the average of the population. And so these elasticity values then maybe can look at not only the average for the entire population, but you can actually you can specify each device as either having the exact same elasticity, or you can look at doing some averaging across the different populations. So for example, if this system maybe had an average daily elasticity of 13%, and when you're creating your population, you could either have all of them be at 13%, or you could have them all have 13% plus or minus 5% on a normal distribution. So there's some lack of knowledge of what that might be, but you can provide diversity in the system if you like by kind of spreading that unknown across it. As far as in the, I see a forum in there about the questions about the tiers. I'm not sure that's written up anywhere, but Frank is going to check for us. And if not, then I will take that as a task to make sure that getting done, so that we can actually get that out in a solid form so that it's clear. Let me just jot that note down. Because yeah, it is a little confusing and it's a little unclear. So I'll make sure that I'll take a look at the documentation this afternoon and see what condition it is and update it to be a little bit more clear. So a little bit more about the specific objects. In this case, now we're going to get into the auction. Some of this might be a little bit overkill, because in the end, a lot of what I would recommend doing with these devices, especially since these are by far some of the most complicated devices that we have in GridLab. And additionally to that, with things like power flow or even our building models, we have other things to work off of, i.e., lots of people have done power flow software, and there's kind of a fairly common and understood way, and there's this, kind of a known language to creating these models. Of course, each one does them slightly differently, but in general, they're very familiar. Same with the residential models. There's tools like Energy Plus that do something along the same lines. So it has this very same feel. With these devices, this is something that we're exploring as we're going, and it's where actually this work, where a lot of our main work is going on. So I will call these experimental objects, because we're experimenting and trying to learn the language of how to create these. At the same time, we're trying to create the control systems that underlie them. So at times you'll see some of these are a little strange or maybe a little outdated, and I apologize for that. And the only reason I can explain is because we're learning as we're going. So just be aware of that as we're going through this. But when we look at an auction object, there's a few basic things that we need to specify. Obviously, the name, that becomes very important because we're trying to direct other devices to find them. So in this case, the name is very important. We need to specify the type of unit that the market is using. So, for example, you can use megawatts or kilowatt hours. Basically, as a way to kind of put a boundary on what these values might be. Our period is how often the market is activated. So how often is information being broadcasted or collected. The latency, we can actually put in a small lag between clearing and delivery. So this is on the back end. Kind of our first approximation of communication delays. So you can clear the market and then put in, say, like a 30-second latency. Of course, what happens then is that every device receives a 30-second latency, so it's not entirely accurate on there. But it was a first attempt at that. We allow some certain special modes, which are like buyer-only or seller-only markets, so that you don't have to worry about the other side of your market if all you care about is, say, getting your buyers to participate. So, for example, doing a buyers-only market is a way to basically represent the stub auction market. Basically, it's just a price broadcast at that point. So just a little bit of ways to experiment. price cap, so you can limit the absolute highest prices allowed. Verbose. This is a special, even though GridLAB-D in general has a verbose setting, there's a special one for auction. I would be very, very careful about activating this because it is extremely verbose. It will basically let you watch everything that's happening inside the market. So all the bids it's receiving, the formulation of the bid curves. It can get fairly massive, but if you are trying to understand what's going on inside of a market, it can be very helpful. Then we have initial prices, initial standard deviations. These are used to what we call bootstrapping the market. And they are only used if our a flag called warm-up is set to true. And this is to basically allow you to precede all of the standard deviations and average prices so that the market has information to work with. And then we have what's called the capacity reference object, and we'll talk a little bit more about that in just a minute here. So the other piece that the auction object is trying to do is collect a number of different statistical information as it's going along. We've made it flexible enough that you can collect any statistics that you would like to related to mean and standard deviation. And so basically when you create your auction object, you can also extend the class to add these different statistics into it. So specifically, you would call something like double, declare whether you want past, current, or current pricing, mean, or standard deviation, and the intervals that you want it to collect on. So, for example, you could do the past price mean for the last 5 days, so which would give you the mean price by using all the information collected over the last 5 days, or you could do the current standard deviation of prices over the last 3 minutes, for example. You can use any of the kind of the standard, units for days, weeks, months, seconds, hours, all those different types of things. Excuse me. And so these are the statistics that the controller objects will then look at to make certain decisions. So there's a number of different auction outputs that are available. Of course, there's the user-specified statistics that we just talked about. You also have access to things called current market, dot clearing price, and dot clearing quantity. So you can get your P and Q from the different market system. You can do the previous market. So in case you want to look at any the previous information to make any decision about the next thing you should be doing. And you also get to find out things like, what was the clearing case? For example, was this a marginal quantity, or excuse me, a marginal buyer or marginal seller? You can even look at things like the marginal quantity or the marginal, those type of things, and pull that information out. So the one we haven't talked about is the capacity object. So this idea again came from the Olympic Peninsula. The idea was that you have a certain object in your system. In this case, let's say it may be a substation transformer, that you want to limit the amount of power flow through for various reasons. Capacity limitations being the obvious one, but there are other cases where you might want to use this. What this capacity object lets you do is specify which object in the system you would like to do that with. So effectively, if you activate this capacity object, it will form a bid on the seller side of the curve that says, well, I would like to limit my power flow through this device to this level. So ideally, what will happen is if your load consumption over the next 5 minutes will be below that capacity, then you'll basically just clear at your bid price, at your supplier bid price. In the cases that we've used with, say, for example, the Olympic Peninsula demonstration, or in our AEP GridSmart demo, this will be the LMP at that location. So basically, the marginal price there will then get passed on to the distribution system to pay the wholesale costs, obviously plus adders and things like that. But and then you have this limitation to say, well, here's my capacity limit, so I don't want to exceed that. So if your load is lying somewhere along this curve, customers are basically going to pay the LMP. If you go above it, you're going to start to elevate the price to limit the capacity to whatever the constraint is on your system. Now, there's a couple of other little things it has to do in there to kind of make this information clear to it. Part of what it also has to do is try to estimate what the unparticipating part of the load is doing on the system. We call this unresponsive load. So basically, you have this set of devices on the system that is sending in bids, that is giving information about the current state of the system, passing that information in, but there's this whole other subset of devices that are not telling you anything. This includes losses on your transformers and lines and things like that. And so really you're running into an accounting error. So this capacity object is making what I'll call a system level estimate of how many devices are on this feeder they're not responding and how much they're going to consume over the next, say, 5-minute market period. We do this by taking a power measurement at the device that we're looking at. Just keep calling it a substation. We take a power measurement through that, and we effectively subtract off everybody in the last market period who said they ran, i.e., say this device to this device right here, and then make the assumption that everybody else was the unresponsive load that is not participating in the market. So what this capacity object is doing is it's really bidding on both sides of the curve. It's going to be bidding in this price limit and this capacity limit, but it's also going to be bidding in this block of buyers who are not responsive to the price bid, to the price system. And really this is a way that we can capture the combined effects of both a market system on a feeder combined with, say, things like critical peak price customers or just fixed rate customers, but then also to couple it with the actual power system measurements in a way that allows us to approximately at least limit feeder loading or substation loading at that device. Now this can be either, again, I keep using substation because it's a fairly natural place to do it, but you could do it on a much smaller scale. So you could, for example, do it at a residential customer transformer that only has 15 customers on it. They could participate in a small market that uses that transformer as the capacity market, and then basically try to limit the amount of power flowing through that transformer. Now, of course, there's a lot of issues that go into that. First is size of the scale of your system. The more participants you have in the market, the less error you end up with because you get diversity throughout the system. As you get that market much smaller, you run into things like synchronization of loads and things like that can cause some issues. And you can also run into some issues with basically asking too much. So if this bid, for example, came in right here, so your capacity limit was at this spot rather than out here, you would basically do what's called breaking the market. You would be asking for more response than is available. All the prices would go to price cap, and then no matter what all the consumers try to do, there's no way they can respond to what you're asking them for. So there's some risk involved with that, but that's part of the fun of trying to explore how this thing works. So just to give you an example of how this capacity object might be set up in an auction. Again, we're looking at giving it a name. This is we're declaring the type of auction it is. In this case, we're doing a full double auction market. The units in it happen to be kilowatts with a 5-minute interval between markets. we're doing some just initialization to stabilize the market, and then we would set something up like, say, for example, in this case, we have a substation regulator that we're looking at, and we want to say, okay, here's the name of the object that we're looking at. Here's the property that we want to look at inside of that object to measure real power. This is the bid price of that power. In this case, this would be, say, represent the LMP price. And then the capacity reference big quantity basically says what's the quantity, what's my limiting quantity. In this case, it's 125 kilowatts. And that's because we declared it in this unit here. And so really this is saying, okay, out of this regulator, we would really like to limit the flow out of that regulator to 125 kilowatts. And here's the price that we are willing to, here's the base price that as long as you don't go above, here's the base price if you don't go above 125 kilowatts, this is what you'll pay. If we start to push above 125 kilowatts, or the desire to go above 125 kilowatts comes along, then we're going to push the price up until we keep the limit at 125. So this is a little bit under the hood about how this thing works. Won't go into this too much, but effectively there's a submit bid function that allows the different objects to bid into the market, and vice versa for the market to push bid information back down into the objects themselves. There's a clearing of the market. Again, you can have access to these through either what's called past market clearing price and quantity, or current market clearing price and quantity. Effectively, it's exactly what it sounds like. Whatever market we are in, which will be the cleared market plus your time period. So your current market will be, say, from 1 o'clock to 1:05. Then your past market would be 12:55 to 1 o'clock. Fairly simple, straightforward. And all these values, of course, can be seen by your recorder objects, or what's more important for what we're trying to do here is they can be delivered directly to your controller object for response. Which leads us into the next step, which is the actual controller object itself. So these controller modes objects have what we call ramp. Again, this is I should restate this, this is a controller designed to work with HVAC systems. So we have what's called a ramp mode, which is very similar to what I showed you previously, this graphic right here with the ramping mode. Or we have what's called double ramp, which is a method that we've come up with in the case of automated thermostats, when you have both a heating and cooling system, where you may have an overlap of pre-cooling and preheating if you're using those. And it's a way for resolving those different conflicts, which I'll go into in a minute here. But effectively, when we're talking about this ramp control mode, this is very similar to the passive response that we talked about before. So basically, the consumer has a base set point, and they're responding to which they would set their device to at average price. Note that this scale on the y-axis is in standard deviations of price, not the actual price. So this allows us to account for long-term fluctuations in price without having to reset the market every few days or so. So it's really looking at the relative price at any given 5-minute market period, not the absolute price. So the way that this is responded, so remember this is kind of a closed loop system, so got to start somewhere, so we'll start with the bid. This device is looking at what the current air temperature is inside the home. So in this case, it's 3 degrees over the desired set point. So this has a certain value reflected on this curve that says, well, we are this high, so I am this willing to pay the price. In other words, I've floated higher than I would like to at this point, so I'm willing to pay a little bit more for electricity. In this case, about 1.1 standard deviations above the mean. That price is then submitted into the market or the auction. The auction clears a price. In this case, the price comes out very, very low. So we actually clear this price at this level, and we adjust the set point to here. So say, for example, if the base set point was 75 degrees and we were sitting at 78 degrees, it would move the set point down to 74, and then therefore activate your air conditioner. And then, of course, you would be paying that market price, which is far lower than average, so you should be getting a deal, basically. And then we have, of course, our limitations to say that customers can say, well, I'll let you take 5 degrees of my thermostat, up to a certain point, and then I'm just done, and vice versa. You can pre-cool me a little bit. I'll be quite honest, we don't use the preheating and pre-cooling modes that often. We found that they're pretty inefficient, and it's hard to, at least in a residential unit, it's hard to accurately predict when you should be using it. In something like a commercial environment, or like some of the larger, like hotel load, for example, there's a significant advantage in doing this kind of pre-cooling. We found, at least with residential, that pre-cooling or preheating setting is not as advantageous as we'd like it to be. But it's there for your use if you'd like it. And again, we have slider settings that allow you to either very quickly set the slope of this response, or you can set every little piece of this together all at once and basically kind of define all the different slopes, define the different Tmins and Tmaxes. I'll show you how to do that here in a second. So again, that was kind of just a broad overview of what this controller is trying to do. Now here's back to how do you actually do it. Again, we're looking at which market do we want to talk to. We set a parent inside the controller, which tells it which device we're trying to control. In this case, we're looking at, say, for example, an HVAC system. So we'd set this as the child to a house. We have the set point that we would like to control. So in this case, it might be the cooling set point inside the home. So this is really a property that we're trying to look for. We're going to set a base set point. So this is basically what would your thermostat be doing if the controller wasn't there. We're going to look at what we'll call a target. So this is the value that the set point is going to be compared against. And what I mean by that is that this is, it's easier to show it on the graphic here. So this would be the base set point. This would be your target. So what's your current air temperature? So typically when we build this for an HVAC system, you would be able to set this set point as air temperature inside the home. I'll show you some examples here. Hopefully it'll become a little bit more clear when there's one that's built with all this value actually in it. And I'll be quite honest, a lot of these, I use a lot of copy and paste with controllers and auctions because sometimes I quite honestly forget what all these different setups are. So we use copy and paste quite liberally on these devices. Your period is ideally, it should be the same period as your auction. It doesn't necessarily have to be. However, I'd recommend that that period is either equal to the auction or greater than or equal to the auction period. And the reason being is that if you make this period smaller than the auction period, then the prices in between two different market clearings are not necessarily clear. This is really the case with stub auctions more than auctions, but ideally this value would be set at equal to your period length of your auction or a multiple of that period length. And GridLAB will actually throw a warning. It will do a test on that and say, oh, well, this is not really the most ideal period. Are you sure this is what you want? And let you know of that. This demand is looking at the property inside the house that is allowing us to estimate what the quantity will be for the bid. In this case, we typically use HVAC cooling load or last HVAC cooling load, which is actually just a register that says, the last time the HVAC ran, we consumed at a rate of 2 kilowatts. And so it stores that information and allows that to be bid back in. Or you can port it to, say, something like the cooling capacity and allow it to bid off the capacity rather than a actual power draw type of approach. Again, Verbose, just like auction, provides a lot of information. And when I say a lot, I mean a lot, so be careful using that, but it does help you look at that information and try to understand what's going on. We also have bid mode, so you can either, effectively, you can tell this controller to bid or not. We plan in the future to have more modes, but right now it's really just on or off. And that allows you to put a controller object like this into your market and respond to the prices, but not bid that price back in. To limit the way that we, all the different connection points and try to make it a little bit easier, we've actually created what we call a simple mode. So if you don't want to do a lot of configuration and things like that, i.e. not a lot of flexibility, we've kind of set up a couple of simple modes that I'll show you here in a second. But then what we have here are, we still need to look at our market and understand what the average price is and the standard deviation of price. That's what these are used for, so you can point to the different targets. A little bit more on the controller. Again, we can specify our control mode of ramp or double ramp. When we do that, we can set either set the slider setting. So for example, if we use slider setting ramp, we can set this value from 0 to 1, and it will set all the T-mins, T-maxes, slopes, all those to some predefined values. If you're using the double ramp mode, you can do this for both heating and cooling. And then the other option is you can set this all by hand. Basically, you define each of them individually. This is for ramp mode. If you were using double ramp mode, it would be heating range low, heating range high, cooling range low, cooling range high. So you'd have to specify all those each individually. So in general, if for initial experimentation, I'd recommend using the slider settings rather than the range and ramps because there's a lot more to it. So again, just really quickly, what we're trying to accomplish for the double ramp mode is there's this case where there's an area of conflict if you're using preheating and pre-cooling that we want to resolve when you're using an automatic thermostat that's using both sides. So we've basically created a couple of different resolution methods that will allow you to either do what's called, we call it Deadband Resolution, where you can basically say, well, we'd like to just pick the midpoint, and we'll reduce the size of pre-cooling on either side. So a slider setting of 0 to 100%. Basically, is comfort versus savings, where 0% is very comfortable. Basically, you will leave no matter what price does, you will not move your set point, whereas 100% means it's our best guess at what the most responsive customer might be. This comes from our information from the Olympic Peninsula demonstration project, and it was kind of the most that we thought customers would actually respond, and that has a limit of Tmax of 5 degrees, Tmin of -3 degrees, with a certain slope setting that a lot of the maximum customers gravitated to in the original experiment. So it's our best guess at what that 100% might mean. So the other resolution that we have is what we call our dominant mode, and this is basically trying to look at, well, since cooling ran last, we're probably in the summertime, so let's activate pre-cooling and turn off preheating. And so it just looks at the last state of the HVAC system and makes a decision about which preheating or pre-cooling mode should be actually dominant at that given moment. Again, what we usually do is just turn off pre-cooling and preheating, so none of this becomes necessary as far as the resolution mode. But you still want to use the double ramp control when you're trying to use a fully automated thermostat for both heating and cooling, i.e. like an auto thermostat. Now, passive controller, again, we've got a lot of different things that are going on there. this is a little not quite up to date. Control mode, we have ramp, probability off, so the direct load controls which showed you before. Here's kind of just a list of all the different properties that you can access, and we kind of went through those a little bit, so I'm going to kind of jump over this and talk. The one thing I want to notice on there, because of the way that this one is built, if you notice the controller object is very built around the auction. It is looking for specific information coming out of the auction, and it is looking to deliver specific information back to the auction. And that's because those two objects are very tied together. Passive controller is built a little bit more flexibly. So you see things like, we're looking for different expectation and observation properties and objects. We're looking for different set points and properties and things like that. And it's all built so that we can respond to not just a price signal, but any signal, so that you can look at any type of device or any type of signal coming out of any type of device and respond to it in an appropriate manner. And the whole reason is that because this device doesn't have to bid back into a market, it's much more flexible in its structure and the way that those can be put together. So here are really just a bunch of examples that we've put together. So in this case, we have a controller object that is attached to an HVAC system that's operating in double ramp mode. So it's got all these different settings. Consider these kind of the minimal level of settings that are needed to operate each of these controllers. Again, it looks like a whole bunch of information, and sometimes it feels that way, but that's why we've set up these examples so that really it becomes a copy and paste issue. Here's a controller for HVAC systems that are on the ramp mode. This is a passive controller that's looking at probabilistic off. In this particular case, it's probably going to be attached to a hot water heater. When I get finished here in just a second, I'll show you one other place where you can get a number of different examples of all the ways that we have used these and validated these different types of controllers. One last thing we want to kind of touch on here is customer billing. So one of the pieces that allows us to really kind of explore this and that we really want to capture is how switching between these different types of pricing schemes or market control systems really affects the customer's bill, quite honestly. So we're looking at different ways of capturing the different billed information, so that as you progress from one pricing system to another, you can look at not only on average how the customer prices is affected, but you can also look at, say, winners versus losers. So if you're interested in things like market fairness or how different rate structures will reapportion the different value streams to different customers, you can start to explore some of these things. This is, for example, what we were able to do on some of our work with one of the demonstration projects we're on. Is we're able to produce not only the average change in bills by switching to an RTP price, but also to look at who were the ones that who were most advantaged by switching to an RTP rate, and vice versa, which gave them information about how to approach different customers in the way that they wanted to maybe participate in these programs. But really, what we're looking at is some fairly standard billing types. We have our uniform bill mode, which is just flat rates. So you have a price. This price can either be just a flat rate, where you could feed in a player or a schedule or something like that. You notice there's this setting called bill day. So this is the day of the month that the bill is calculated or processed. So in this case, this is always done at 3 a.m. on that day. So in this case, this meter, which is where this information is embedded, is inside the triplex meter. We cover this in the market module because a lot of this information will come from the market module. But effectively, this is the triplex meter that your house might attach to, and is supposed to represent your billing meter. But really, this bill day will be the day of the month that you want to process the bill. So in this case, it's being processed on the 1st. So really, you're going to be processing the bill from the previous month on the first day of this month. One note here is that it will only work through days 1 through 28. It doesn't accept 29, 30, or 31 because it gets fairly confused about February. So we've just kind of made that limitation on there. So, but if you're trying to process your bill, say at the end of the month, really your bill day would be 1. So bill day 1 says process the last month. You can do your monthly fees on there and that type of thing. So you can do a standard flat type of fee. So this is just doing a kind of standard calculation, nothing crazy or anything like that. Default values, dollars per kilowatt hour, things like that. Then we can move on to more what we call it hourly, but really it doesn't even have to be hourly. It can be minute by minute changes. But really what it's doing is it's processing real-time rates. So you activate this bill mode hourly. You tell it what its power market is. So again, this would be power market, say like market 1 or my market or whatever your auction object is that is broadcasting prices to your controllers. And it will use that broadcasted price to calculate the bill rather than a fixed rate or anything like that. The third one is tiered mode. So again, we have a lot of flexibility into this. So this is more like block rate type of approaches. So if you wanted to say like have a some have an incline, some have a declining price blocks. But in this case, for your first 100 kilowatt hours, you're going to be spending 15 cents a kilowatt hour. Up to 500 kilowatt hours, you'll spend 18 cents a kilowatt hour, and up to 1,000. Excuse me, I said that backwards. Your base price is going to be 10 cents a kilowatt hour. Once you hit 100 kilowatt hours, you will start paying 15 cents. Once you hit 500, you'll start paying this. Once you hit 1,000, then you start paying 20 cents a kilowatt hour. So it's just your standard block rates type of idea. So this is what we use for flat billing. This is what we use for our kind of block ratings. This mode will work with anything you do in the auction. So it can be time of use, critical peak pricing. It can be real-time pricing, whatever that might be. It's really just looking at the market to get that information and calculate the bill. Now to extract that information, you can of course hook a recorder on each of these devices, but that can be pretty tedious, especially if you have a system that has say 1,000 customers on it. You really don't want to be putting 1,000 recorders on there just to get one piece of information once a month. So we've created an object called bill dump that you can run at any given time, and it will take a look at all the triplex meters. It will grab their monthly bill and their monthly energy consumption and dump it out into a single CSV file that just has the list of all the different customers, all their different energy consumptions, and all their different monthly bills. Now, one note about this, good question, so I will talk about that right now, Simon. So this bill dump is scheduled to basically capture the bills once per month. So for example, if you were running an annual simulation, you would want to capture this at the end of every single month. So for example, if you're looking at this runtime right here of 2000-01-01 at midnight, this is actually going to capture the bill for December of 1999 because it's always going to be looking at what the last customer's bill was, because you don't actually know what the current customer bill is because it's being formulated right now. So if you were creating an annual simulation that from say January 1st to December 31st, the very first bill dump you would create would be something that would look like this. It'd be actually on February 1st, and that will produce the effectively the Jan bill. To be a little more specific there. So again, if you're running this for 12 months, then you will want to create 12 different bill dump objects. But what that does is very nicely puts these out in very simple, comma, and delineated files that you can then post-process and merge together and use that information however you like. Very handy, very useful. I use it quite a bit. So beyond this, there's a number of exercises that we've put together here that you can kind of go through. A lot of these are just kind of to learn how to play with the different systems and put them together, put them on a GLM and those type of things. When you look at the structure of the Module 4 that I just put up there for you, there are a number of different examples. So for example, we have example price player, just what this might look like and things like that. We have examples, just an IEEE 4-node system that I believe has this is just the base one that you can use to attach a market to. There's some examples for the demand response that just happen to coincide with these exercises. You have exercises 1 through 3. So these are the examples. Basically has the entire model built for you, so you can take a look at that. This has basically a pre-built model in this case, because the one we're looking at for exercise 1, it's a passive demand response system. It has a stub auction built on it. Again, it has players, recorders. This happens to be a climate for Seattle. And basically, then you can come down and look and say, okay, here's an object house. Has a cooling type electric, so it's a heating type heat pump. But in this case, it has a passive controller that is going to be doing some kind of modification on the cooling set point. And then again, for the heating set point. So in here, you can see all the different ways that we've put these different things together by looking at the different examples that are in here. Yes, that's a good question, Simon, about using a collector to collect bills. That was what we originally had started to do the first time we put this together, and then quickly realized that we didn't just want the average or standard deviation information. We actually wanted all the individual bills so that we could look at, again, that winners versus losers type of approach. So yes, you can use the collector to collect that type of information just like you do any other property. But in this case, we wanted access to a lot more information than just being able to get like average or standard deviation or max or min or those types of aggregate values. What we've added into, I believe into version 2.3, which is coming out here in the next few weeks, we've added what we call a group recorder, which allows you to effectively do what we do with the bill dump on any type of property. So I could go out and say, I want every single cooling set point for every single house every 15 minutes. Creates massive amounts of data. It slows down your simulation significantly, but at least it adds that flexibility. But the whole reason for the bill dump was so that we could try to capture that information in a less aggregated form, like the collectors do. So as you work through these different exercises, again, all the different solutions are on here so that you can kind of take a look at those and kind of work through different ways and styles of putting them together. We've also included more solutions to, I believe that are these exercises. So you can look at how would I formulate an RTP bill. So here's my auction. You can see in this case we're, again, initiating the price and the standard deviation and things like that. But then when we come down to triplex here, we can take a look at how this triplex meter is put together so that you can bill in an hourly format. It's looking at this power market, billing on the first day of the month, giving it a fee. And we can see we come down here and we create a bill dump and a volt dump just so we can grab the entire system information at the end of the simulation. So all these different examples are built into Module 4 here. We even left the executables, if you're in Windows, either 64-bit, so that you can just drop your files in there and run them. Again, this class is based off of version 2.2, and that's what these release versions are here, these executables that we have built. And it's also that, although it's, we're coming out with version 2.3 here shortly, which does add a fair amount of capability to the market, although not a lot. This class, as I mentioned, is built around version 2.2 and the capabilities that are in there. There's one more example in here, which is the IEEE 13 node. These other ones are slightly simple systems, but what this allows you to do is experiment a little bit with a bunch of different styles of market systems. So it takes this IEEE 13 node system, and notice I call it a modified system. We did some slimming down of pieces of it just to make it a little bit easier to work with. But what we've created is a MATLAB script that you can run out of MATLAB, and allows you to set a various number of different types of settings inside there. So besides market, there's a number of other ones, things like you can do battery storage, centralized versus decentralized. But we can do things like activate markets. So you can use cases where there's no what I'll call active markets in there, or you can do bidding or non-bidding type of markets. Sorry, you can do your base case bidding market or a non-bidding market. This is a bunch of information that basically sets up the market info. So, what's the name of, true or false, is this going to be a market? What's the name of the market? And what's my period? What statistics am I going to collect? What's my average slider setting? And then what's my price slider that comes in? So this allows you to kind of just quickly set up a market, build some of the parameters in there without having to deal with all the different the syntax of getting all those pieces put together. You can also do things like activate the different billing types, none, flat, tiered, or hourly, adding your fees, basically your flat rates, all of your different tiered energies, things like that. So again, kind of a way to, if you're using MATLAB, to kind of very quickly build some of these simulations and look at how the syntax might come out, so that you can get a better feel for how you might do that. The other place that we've put some of these examples out there are out on the SourceForge account. You can do the SVN browse on the SourceForge. In fact, let's go through it that way so I can show you guys how that looks. So if we go to GridLAB-D, just the SourceForge page, we can go to code SVN browse, or of course if you've done an SVN download, you already have access to this, but under taxonomy feeders and population script. Again, this is a MATLAB script because this is what, basically this is what we're very familiar with. There's a file called feedergenerator.m that you can go and either download or view via the repository here. It's being slow, so we're just going to skip it. We'll open up this feeder generator file. Apologize, give MATLAB a second here to wake up. So again, very similar to that script I just showed you, this is one that's we've created to work with our prototypical feeders. It allows you to do a whole number of different types of technologies, anywhere from, you can see here, if you just change your technologies, then you can go from a base case, you can do CDVR, automation, or FDIR. You can do time of use critical pricing with and without technologies. You can do direct load control, thermal storage, and PHEVs and generators, which Frank will get into shortly, probably in about, I think, we're scheduled for about 3 or 4 weeks from now. But all these different technologies, effectively all you have to do is change this technology and then make sure that you can find the right configurations. In this case, we've done a bunch of configurations that allow us to look for the right files that we might be looking for, what directory that's located in. So in my case, for me, I want to look at these two different taxonomy feeders. They're located in this directory. Once you have that set up, you should literally be able to just run this script on a certain technology. So let's say let's look at time of use critical peak pricing. If we run that, I get a little bit of warnings because MATLAB has changed the random number generator again, as they do every other year. But it'll run through these cases. It's reading in the base R1 1247.3 file and then modifying it to be technology 4, which is in this case time of use critical peak pricing, and will create a whole new GLM that has all those features in it. So if I go and look at where I asked it to output to, which I'm sure I can't remember what that is right now. Let's take a look. That should just be in here. So if I pull up this file, this now is this taxonomy feeder R1 1247.3 with a bunch of new technologies added to it. It's got, kind of pulls in all the schedules that you need, sets up the clock, all these different things that you might notice. This is an annual simulation because this was for analysis work that we were doing. But if we go and look at something like a house, we can see here's our object house that we've built with all of the parameters that we wanted. We've created a zip load that happens to be what we're calling, quote unquote, the responsive load. So these are the loads that are going to be affected by a change in price. So this might be things like, say, your dryer or your TV or these other devices. We've also created a load that's called unresponsive load, which is what we're calling the pieces that are not affected by price. In this case, it would be things like your refrigerator duty cycle. And then we add the water heater object, and of course the HVAC system is embedded into the house. So we basically have 4 specific loads on this house. And we set up all the different controls that we might have for, in this case, time of use critical peak pricing. So we build a passive controller that's in elasticity mode, and set up all the different tiers, all of our different elasticities that we might want, which critical day. We have this thing here called price offset, which basically allows us to do if we're doing some price comparisons. So when we look at, say, first tier price, it's basically looking at price above 0.06 plus 0.01. Basically, it's there for coding reasons. This is the default if you don't include it, so don't worry about that too much. But then, it looks at, okay, here's our water heater. Here's how we build a passive controller to do some response to a probability off event. So basically, when you go into critical peak pricing, this guy should be turning off about 50% of the time, is roughly what that will come out to look like. We can also look at some of the pool pump controls, for example. So here's a object zip load that we basically created to look like a pool pump. It's basically doing some duty cycle running on there. We've activated it to be a 240 volts rather than a 120 volt circuit. And then we activate what this is called our recovery duty cycle. So in comparison to the normal duty cycle, we want to say, well, during recovery period after an event, how active should I be? And then we built this passive controller that, again, looks at all the different pieces and then will determine how long that recovery period needs to be to actually recover the amount of lost time run. And there's the control mode that I couldn't remember. It's just called duty cycle. This could also be control mode off, where effectively you would set it up exactly the same, and when market price reached third tier price, it would just turn that device off. So again, this is just these examples are what we've set out there to show the ways that we have used this model. These ones that I would say are in this MATLAB script that you have available to, these are what we would call very validated models at this point because we've used them for analysis that we've provided to DOE. So these are probably the most, probably the best resource to show you examples of how to put those together. And then what I'll do over the next day or two is I will go out and try to update the wiki page to reflect some of the things we talked about and some of the questions that came up today, especially on the time of use tiers and what those different things mean and how you set up different configurations. So beyond that, I would definitely recommend people who have an interest in using this market is to walk through some of these exercises and give them a try and see what issues you will run into. Some of these are specifically designed to make you run into issues. So definitely try to walk through them in a dedicated manner if you think you will gain something from it. If you just skip straight to the solution, which those are provided there, you don't quite. It doesn't quite walk you through all the things you need to learn. But you know, so try to think of these as teaching exercises that walk you through different errors that we have run into quite often, and to kind of highlight some of those errors to kind of help reinforce what we talked about today. So beyond that, I will open this up to questions at this point. So I don't think we might need to unmute everyone, Frank. I don't know if we have everyone muted right now.
I haven't muted. They should be able to override it, but
there we go. Good job, Frank.
figured it was easier to do it manually than basically blanket mute everybody and unmute them.
Yep, exactly. So are there any questions? Anybody have any comments, any gaps that I hopefully, well, I'm sure I left some gaps in there because there's, again, this is a fairly big and complicated module, and I have no doubts there's tricks I did not include in there, but I tried to remember as many as I could. But if there, you know, if questions creep up, feel free to shoot me an email or you know, ask questions on the forums. We'll try to get them answered up. If you're, you'll walk into these exercises and things. Well, great. I guess if there's no questions, we'll kind of wrap up things today. I think Frank and I will both be on here for another 5 or 10 minutes if any questions come up. But otherwise, we're finishing up for today, and we'll try to get this recording out onto the website here within the next few days so that anybody else who wasn't able to attend, which would not be any of you guys, will be able to have access to that. So again, thank you. Any questions come up, let me know.